Okay, number 10. A flight attendant pulls her 70 Newton flight bag a distance of 253 meters along a level airport floor at a constant velocity. Constant velocity must mean there's no acceleration. The force she exerts is 40 newtons at an angle of 52 degrees above the horizontal. So we're supposed to find the following. The work she does on the flight bag, the work done by the force of friction on the flight bag, and the coefficient of kinetic friction between the flight bag and the floor. So there again, we need to draw a sketch picture. So I move my book out of the way here. So here's the picture I started out with. Okay, here we go. So this is number 10. So this is the suitcase, or the stewardess's bag, and I've got mg going straight down. They already told us what mg is. So they already multiplied the mass times 9.81. And then here's my applied force. My applied force was 40 newtons. All right, 40 newtons at 52 degrees above the horizontal. So there's a horizontal, I draw 52. So now we need to draw the component vectors, always the component vectors. So let's do that. I'm going to draw the y1 is going to go up. So this is the applied force. Applied force. So in the y direction, the force applied in the y direction is going up. And we see that it's opposite to the 52 degrees. So this one's going to be 40 sine of 52. And in the x direction, that's this one here, is going to the right. To the right, and I have force applied in the x direction, supposed to be an x, is 40 cosine of 52. All right, there we go. All right, so we want to know what is the equation for work. They want to know what work is. We'll go ahead and write here. Well, work is the force times the distance times the cosine of theta. All right, so notice the force times the cosine of theta, that's this one right here. That's FAX. Because if you're going to be dragging this box this way, the only force that's actually helping you to move it is the cosine one. So this vertical one you could say is being wasted. All right. So that's why this equation is the work being done on the box is just the force that actually is helping it to go horizontally. Okay, so this is a good problem to show you why that equation is true. All right, so we can plug that in. Let's see, I'm going to move it over here. So work, FD cosine theta. All right, it's 40 newtons. 40 newtons times the distance, and they told us the distance was 253 newtons, meters rather, meters, that's my Newton meters, times the cosine of 52. Okay, you plug that in and you get 6,230.5 joules. My J's kind of look like 5s. All right, so there it is. That's the work done on the bag. Okay, on the bag. Work done on the bag. The next question was, let's see if I can read it exactly how it says. What's the work done by the force of friction on the bag? All right, so we didn't draw. What's missing here in this picture is our force of friction. The force of friction, it's moving, so it's kinetic, opposes the direction of motion. The box is going to the right, so therefore my force of friction is going exactly to the left. So you can see from the picture, we have no net, the acceleration is 0. So this magnitude of force of friction has to equal this magnitude. All right, so therefore the work is going to be the same. It's just in the other direction. The magnitude of the force is the same as FAX, but it's in the other direction. So it's 40 cosine 52, but in the negative direction. So the work done by the friction, work done by the friction is opposite direction. It's just negative 6,230.5. You could have plugged it in, but you would have gotten the same thing. All right, so the last thing, I think I'm gonna have to unzoom a little bit here. The last thing they want to know is mu k. So I write down the equation, always mu k, and I know that the one that goes in the bottom is the normal force. Oh, so the upper one must be the k one. All right, so we figured out what the Fk is, except that it's negative. It's the same magnitude. This one's the same magnitude as this one right here. And do we know what Fn is? Do we know what Fn is? So here we have to figure out what Fn is. Fn, I'll draw it in here. I didn't draw it in. Fn is this one going up. You guys are getting good at this for the last test. So we notice that we have three vectors in the y direction. We have Fn going up. We have Fa applied in the y direction, and we have Fg. And there is no net, or the net forces, all right, right here, the net forces in the y direction is 0. If that's true, the net forces y direction is 0, then all the vectors going up have to equal the vectors going down. All right, so let me write that down over here. So Fn, that one's going up. Fay is going up. F applied in the y direction is going up. Those two combined must equal Fg going down. And we'll have equilibrium. So now we need to solve for Fn. This is just like the one you guys had on your last test. Fn is going to be, I subtract the applied force in the y direction of both sides, so I have Fay. All right, so let's see, Fg, they told us was 70 newtons. 70 newtons minus Fay is 40 sine 52. 40 sine 52. And when you plug that in, you get 38.47956. I must have written as many as I could. Okay, so now I've got the Fn. That guy goes right here. And I got the Fk, the force. The force was just the 40 newtons times cosine 52. So this one right here is the 40 cosine 52, 52, all divided by this stuff we just figured out here, 38.47956. And when you divide those, you get 0.63998. So it's about 0.640. 0.640. That's our coefficient of kinetic friction. All right, so let's look at this again. So you notice that everything you've learned before comes into play still. We're just adding a new parameter, and that's called work. So we know that work is the force times the distance times the cosine of the angle. And now you see why. In order to drag the suitcase horizontally, your vertical one's not going to help you. Only the one that's going horizontally is really going to give you work being done to the suitcase. All right, so we're able to figure that out just by plugging it in. We had 40 newtons times the distance times the cosine 52, and that gave us our work was 6,230.5 joules. All right, that's the work done to the bag. But like everything, there's always friction opposing the motion. So there's work done by the friction, and that's the same magnitude, just opposite direction. All right, then I want to know what the coefficient of friction is. We write down the equation, coefficient of friction, the kinetic force divided by the normal force. So the kinetic force, we realize that the kinetic force has to be balanced for all the x vectors. There's only two of them. There's a equilibrium there. So we know Fk needs to be 40 cosine 52. It's just a negative. But there is no polarity in coefficient of friction, so I don't worry about the sign there. Now, Fn we had to figure out. So that's when I had to look and see how many vectors that I had in the y direction. I had 3, so I needed to make sure I had equilibrium. So the one going down equals the 2 that are going up. That's why I wrote down the one going down is equal to the 2 going up. And this is how I figured out the normal force. So to get normal force by itself, I subtracted Fa applied in the y direction of both sides. Here it is, mg, 70 newtons. And this, oh, by the way, is newtons. So that goes in the denominator, put in the Fk in the numerator, and we figured out that we ended up with 6.63998. And so the coefficient of kinetic friction is 0.64. All right. So that's it for now. I'll see you next time.